Reconstructing a curve based on given samples with no additional information other than the position is difficult, considering that no connectivity information is present. The reconstruction usually implies generating a graph on the input points and choosing specific edges to recreate the connectivity. We introduce a new method for curve reconstruction based on a combination of Delaunay triangulation and the spheres of influence graph, which is also known as SIG. Our method is inspired by the connectivity algorithm, replacing their starting graph with a SIG-based graph and then enhancing it. We filter edges from the Delaunay triangulation, which are also in the SIG. An edge is in the SIG if it is shorter than the sum of distances of its vertices nearest neighbors, as illustrated by overlapping circles. We eliminate leaf vertices by adding their shortest incident Delaunay edge to the graph. We remove longest edges from vertices with degree more than 2 until their degree becomes 2, as long as no new leaf vertices are created. We connect the graph into a single connected component via a disjoint set and apply a boundary closing heuristic in case of holes. We find vertices with degree greater than 2, which means that they are non-conforming, and add incident exterior triangles as candidates. We sort candidates by the least increase in the total boundary length of the curve. This is computed by adding the length of new edges and subtracting the length of removed ones. When a candidate triangle is added, we add all of its edges to the current reconstruction. We then remove interior edges that are not part of the boundary. We first find interior vertices, i.e. isolated vertices, and add incident triangles in a priority queue as candidates, sorted by the least increase in the boundary length. We add a candidate triangle by adding the edges which are not already present in the graph and removing those that were part of the reconstruction. This procedure exposes the interior vertex to the boundary. Our method performs best for manifold reconstruction compared to state-of-the-art algorithms. Furthermore, the SIG and Delaunay initial graph computation has an accuracy comparable to state-of-the-art algorithms for curve reconstruction, having the additional advantage that it can also reconstruct multiple curves and open curves. For dataset with sharp corners, the performance is still comparable to existing techniques, being only superset by Gatang, which specializes in sharp corners. The results have been computed using the 2D points curve reconstruction survey and benchmark on a subset that interpolates all input points. We propose a reconstruction method based on the SIG for boundary reconstruction of a set of two-dimensional points. The SIG improves on capturing proximity connections between the vertices and does so without requiring a specific number of neighbors as parameter. Together with steps from an existing method, it correctly reconstructs the boundary of the input set in more cases than the reconstruction state of the art. Current results are promising, encouraging further improvements of this approach. We hope you enjoyed the presentation. Thank you.